gas laws. We're gonna do 2 lessons in one day today. So we're doubling up. So that way on Thursday, we can do board races.
Oh no.
Wait, do we have a test Friday?
We have a test Friday, it's a quiz.
Will we get extra credit if we win?
You'll have the option. No, there is no note card this week.
Because it's a quiz.
It's a short, like 10 question quiz, if that. I don't even think it's 10 questions, to be honest. It's probably gonna be like 5. How many points is on Miss Willard's skill checks?
5. Oh my gosh.
Like 5.
How many questions are there? 5 questions?
Yeah, but she doesn't give you like half points.
All right, we'll do that.
No.
5 questions.
Please don't.
No
I
extra.
get 1 out of 5s and my
No.
whole
I'm done. I'm
Yeah,
done.
you get retaken it.
Oh, that's too much work.
Looks like you have to give us half credit. We're halfway.
I'll give you partial points. Okay, the first gas law we are going to talk about falls under the category of the combined gas laws. Yesterday, we looked at temperature and pressure a lot. And we looked at really converting between the units of those pressures and temperatures. But today, we're going to apply them. How can we look at pressure and temperature along with its siblings, volume and moles, to determine some aspects of gases, different aspects of them. The combined gas law is a combination, that's where you get the term combined, of 3 smaller gas laws. The first of which is Boyle's law. Now, Grunkle Boyle, it's great Uncle Boyle, he was an expert with pressure and volume, and that's what he decided to look into. He wanted to look at the relationship between pressure and volume. Have you guys heard the term direct and inverse relationships? If something is directly related to it, what that means is as one thing goes up, the other thing will go up. If one thing goes down, the other thing will go down. If it's inverse, well, that's opposite. If one thing goes up, the other thing will go down. If one thing goes down, the other will go up. Boyle wanted to look at what would happen with pressure and volume as we changed it. I have a balloon. Does everybody see my balloon? It's a very fancy blue balloon.
Did you get that from art class?
No, I stole it from our storage closet. Pretty sure it belongs to Mrs. Corin, but I don't know.
Right. Right.
All right, here's my balloon. Would we all agree that this balloon has some volume to it? What? I don't know, because I'm not measuring it. And it has some pressure on it, right? There's the gas that are in here. They're pushing on the outside of the balloon, and that's what gives it the shape. Do we agree? Okay, what happens if I decrease the volume? Okay, I smash it.
Spreads out.
What happens to the pressure?
Pressure gets higher.
The pressure goes higher. If I keep smashing and smashing and smashing, what's going to end up happening?
Pop.
It's going to pop. So what's happening here?
The pressure is getting too much for the volume.
It's gonna pop.
Right.
Make this little chart. As volume went down, what did we say happened to pressure?
Went up.
Pressure went up. Okay, look at my balloon again. It's a pretty low volume, do we agree? Do you think that this plastic, the rubber, has a lot of pressure on it right now?
No.
No, it does not. But now, with just a little bit of gas, I increased the volume. Okay, it's a little big. Would you say that the pressure went up or down? If I increased the volume, that's an example. Let me do this. This will work a little better. Okay. Right now, my bag has the exact same amount of air. A lot of pressure, not a lot of pressure. Okay. Increase the volume. A lot of pressure, not a lot of pressure on the sides of the bag. Not a lot. It's inverse. The point is that it's inverse. It's opposite. There's really not a good way to do that unless I have like some fancy machine, but I don't have that. But what's happening is as volume goes up, pressure is supposed to go down. In the gist. I will also play with this a lot. I've been playing with it all day. It really irritated my third period, but I don't really care. And we say that this is an inverse relationship. Meaning, as one thing goes up, the other will go down, and vice versa. Cool?
Yep.
Boyle also decided, you know what, how can I apply this mathematically? And so he made the very first gas law, P1 V1 equals P2 V2. Cool? That's Boyle. The next guy, his name is Charles. Charles, a little more boring. He's not very original. What he looked at, instead of pressure and volume, he looked at volume and temperature. Volume and temperature. If I take a balloon and I put air in it, have you guys ever put a balloon inside of a refrigerator or a freezer?
No?
Never thought of that one before.
You guys had bad childhoods. My goodness.
Sure I can.
Okay. What happens if you put a balloon, you fill with your air, and you put it in a freezer, it shrinks, it shrivels up. Because, here's the thing, as the temperature of air goes down, or temperature of a gas goes down, its volume will also go down. This is called a direct relationship. It's a direct relationship because both of the arrows, both of these, when these change, go in the same direction. As volume goes up, temperature will go up. As volume goes down, temp will go down. That leaves me for my last guy. You get one chance to laugh, and I don't want to hear you laugh again. His name was Gay-Lussac. Gay-Lussac, not very original, even less original than Charles, decided to look at pressure and temperature. Think of your car tire. As it gets cold outside, what happens to your tire pressure? As it gets hot outside, what happens?
It stays the same.
It goes up. Temperature will go up, your pressure will go up. So for Gay-Lussac, as pressure goes up, temperature goes up. And as pressure goes down, temperature goes down. Is that direct or indirect? Or inverse?
Indirect.
Direct.
It's direct.
Right.
Mathematically, we say, or we can look at this like this. This like this. That made a lot of sense. We can look at Gay-Lussac's law using this gas law equation. Charles is very similar, but with volume instead of pressure. Cool. Individually, those are all fine, great, handy dandy, whatever. Instead of remembering all three of those, there's an easy way to use them together, and it's called the combined gas law. The combined gas law takes this guy, gets this guy, smashes them together, and becomes this guy. P1 V1 over T1 equals P2 V2 all over T2. That's what we're going to use today. The good thing about the combined gas law is that your units can be a little flexible. You don't necessarily need standardized units. Whereas the ideal gas law, which we're going to talk a little bit, or hear in a little bit about, we will look at specific units. We're going to do two examples using the combined gas law today, and then we're going to switch gears to the ideal. Cool?
Right.
The combined gas law is all about using mathematics to solve for different variables. Let's look at the first fact. A gas occupies 2.50 liters at 1.00 atmospheres. What will it occupy at 0.800 atmospheres? Word problems. We always start our word problems the exact same way, which is making a list of my givens. Look around you. Is anybody not here? I think there's all of you. Okay. When I read this, I always want to start with my given. The first given I see is that gas occupies 2.50 liters at 1.00 atmospheres. Liters, start there. What type of unit is that? Is that a volume, a pressure, or a temperature? It's a volume. Liters is volume. Here's the question though, because if we look at our combined gas law, look, there's two volumes. There's V1 and V2. Do you remember what the ones and twos mean?
Final and initial.
Remember, twos are finals, ones are initials. Context clues of this problem is 2.5 liters volume 1 or volume 2? It's V1. It's the initial. 2.50 liters, that's the initial volume. So this is V1 equals 2.50 liters. Hey, and it's paired with 1 atmosphere. Atmospheres, is that pressure, temperature, or volume? Pressure, we talked about it yesterday. Is that starting pressure or final pressure? Starting, so that's our P1. Adam. What's my final given?
Pressure.
0.800, what is it? Huh? P2, it's atmospheres. So that's our P2. What are we solving for? V2. After I write my list of givens, I like to write my equation. My combined gas law equation, P1 V1 all over T1 equals P2 V2 over T2. The way that you know you're using the combined gas law equations is if you're using initials and finals. The other gas law that we're going to look at here in a little bit, there is no initials and finals. It's just standard. If you're using initials and finals, you immediately should be thinking combined gas law. Cool. Hey, but my problem, look at my formula compared to my givens.
We're missing a T.
We don't have any temperatures. Does everybody see that? There's no temperatures in my given list. There's no temperatures in my problem.
Right.
Here's the magic of the combined gas law. As long as you don't have a final or an initial for that unit or for that variable, you just pretend it's not there. In our case, we just get rid of the t's. And we become P1 V1 equals P2 V2. Hey, isn't that one of the baby laws that go into this? That's Boyle's law. That's the magic of the combined gas law. And from there, it's a plug and chug. We would have 1 times 2.50 equals 0.800 times V2. And you would solve for V2.
3.13.
Huh?
3.13.
Which I guess is 3.13. What's my unit though?
Liters.
Liters. Feel good? And I could do that. I could give you temperatures instead of pressures. There's a lot of different ways I can mix that around. Let's look at one more. You don't have to write the whole problem. Just write your list of givens. Can I erase this? A gas has a volume of 800.0 milliliters at 23 degrees Celsius and 300 torr. What would the volume of the gas be at 227 degrees Celsius and 600 torr of pressure?
You got nothing.
See if I don't hit Kinley this time.
Just, what did this time?
Last time I hit Lily, so I got it. Okay. List of givens. My first given, what is it? Somebody.
800 milliliters.
What is that? Volume V1. What's my next given?
Temperature.
Temperature.
1.
What is it? 0.0 what?
Degrees Celsius.
Gossin, what's my next one?
300 torr.
Which is?
Pressure.
Pressure 1 or 2?
1.
Good. Damien, what's my next given?
227 degrees Celsius.
Which is?
Temperature. T2.
Teachers, for an interruption, just real quick, please see your email about lunch today. Thank you.
T2.
Is the helicopter still coming?
I have no idea. Sorry, I'm reading this email. Okay. All right. Yeah, T2 equals 227 degrees Celsius. Miss Nybert, what's my last given?
600 for PP.
Good. What am I solving for then?
V2.
V2. Megan, you want to come do it on the board?
No. She can't even see the thing. She don't even know what she has to write.
Yeah, it's not a great setup.
Right.
Just tell that we're gonna move all the way over.
I mean, we could.
Using the smart brain.
I'll fix it during lunch. Maybe.
Can you even see the board?
Normally, the people that sit there first and third period, they just use their Chromebook to look at the PowerPoint. I will not lie.
That's so much extra work.
I didn't design the place. I just have to live with what I got. P1 V1 equals T or over T1 equals P2 V2 over T2.
I can't see the board right now. You're right that way.
What are you looking at?
I'm trying to. I'm still on the givens.
You can get them from the prob. You can get them from the prob shop.
I don't know.
Rob, child.
No prob
Why
shop.
do you have them all mixed up?
What do you mean?
You have V1, T1, P1.
I just
you have
wrote them in the
T2,
order that we read them.
T2.
I just wrote them in the order I read them from the problem. Hey, is there anything that I can cross out or ignore?
No.
No, because I got one of each at least. So plug them in.
It's the same thing as one.
Do a little algebra. Solve for V2. Tell me what you get.
Wait, I don't know if I did.
Huh?
I don't know how to do this.
The algebra? Okay, well, we need to get V2 by itself. I would start my algebra here by multiplying both sides by 227. Which gives me 2.37 E6 equals V2. Sorry, 600 times V2. Divide both sides by 600. To get 3.95 E3 equals V2. We're solving for V2. What's my unit going to be here?